This lecture is about matrimony. Actually, it's the first of 3 lectures about a problem from the domain of databases called transaction commit. Transaction commit is a very simple problem, but it is about computer systems and not Hollywood action heroes. Jim Gray was a computer scientist who, in the words of his Turing Award citation, made seminal contributions to database transaction processing research. I had the privilege of knowing Jim for many years. He used to describe transaction commit in terms of a wedding. I learned long ago that if Jim did something, it was the right thing to do. So this lecture begins with a discussion of weddings.
Here's how an old-fashioned wedding goes. There's the bride, let's call her Anne. There's the groom, let's call him Henry. And there's Thomas, the minister. The minister begins by asking, Henry, wilt thou have this woman to thy wedded wife? Let's make it more modern. A 21st century minister might say, Hank, are you prepared to commit to this relationship? To which Henry would reply, I'm prepared. The minister then asks, Anne, are you prepared to commit to this relationship? And Anne replies, I'm prepared. The minister then says, you're now both in a committed relationship. What can go wrong in a wedding? When the minister asks one of them, say the bride, are you prepared to commit to this relationship? She might answer, no. The minister would then abort the wedding. Here's another way the wedding can go amiss. Both the groom and the bride might say they're prepared, but someone else at the wedding might object. The minister could then decide that it was a valid objection and abort the wedding. What does a wedding accomplish? A wedding begins with the bride and groom possibly unsure if they should be married. It allows them each to decide if they're prepared to commit to the relationship, or if they want the wedding aborted. It should finish with them both believing they are in a committed relationship, or both believing that the wedding was aborted. It should be impossible for them to disagree about the outcome. What function does the minister perform? His job is to implement the wedding. He's part of how the wedding works, not part of what the wedding is supposed to accomplish. We're going to write a specification of a wedding, a specification of what a wedding should accomplish, not how it's actually performed. What, not how. The specification mentions only the bride and groom, not the minister, who's part of how, not what. Here's the state transition diagram of each of the 2 participants, the bride and the groom. Each participant starts in the state of being unsure about what he or she wants to do. From that state, they can go into either the prepared or the aborted state. From the prepared state, they can go to either the committed or aborted state. They remain forever in either of those 2 states. We can generalize all this to a really modern wedding, one that's not limited to just one bride and one groom. We can have any number of participants. Each participant has the same permitted states and state transitions as before. We cannot allow one participant to believe the relationship is committed and another to believe it was aborted.
In transaction commit, a wedding is replaced by a database transaction.
The transaction is performed by a collection of processes called resource managers. The transaction can either commit or abort. The transaction can commit only if all resource managers are prepared to commit. The transaction must abort if any resource manager wants to abort. All resource managers must agree on whether the transaction committed or aborted. The execution of a transaction commit is just like a really modern wedding, which can have many participants. A resource manager corresponds to a participant in the wedding. The state transition diagram of each resource manager is the same as that of each participant in a wedding, except that the unsure state is traditionally called the working state of a resource manager. We now see how transaction commit can be specified in TLA+. So you can view the spec while watching the video. You will first open the toolbox, create a new module named tcommit, and copy the body of the spec from the web page and paste it into the module. Stop the video and do this now. You'll see that the spec has lots of comments. I'll discuss comments later. Now, let's look at the spec without any comments. The spec is in module tcommit. It begins by declaring rm to be a constant, which means that its value is the same throughout every behavior. The constant rm represents the set of resource managers. What tells us rm is a set? In TLA+, every value is a set. Even values like 42 and the string ABC are sets. But the semantics of TLA+ don't say what the elements of the sets 42 and ABC are. So the TLC model checker will report an error if it tries to evaluate an expression like 42 is an element of ABC. Next comes the declaration of the spec's single variable rm state, followed by the type invariant that describes what values we expect rm state to be able to assume. We prefix standard names like type-OK by TC because in a later video we'll be talking about two separate specs. The value of rm state will be an array indexed by the set of resource managers, where rm state of R describes the state of resource manager R. This is the TLA+ notation for the set of all arrays indexed by elements of rm, with values in the set given by ... where ... is this set, whose elements are the four strings working, prepared, committed, and aborted, which represent the four possible states of a resource manager. The right arrow is typed -> in ASCII. The initial predicate tcinit asserts that rm state equals this expression, which is a TLA+ notation for the array with index set equal to the set of resource managers, such that the array applied to rm equals the string working for every resource manager rm. This is the TLA+ syntax for an array-valued expression, where this maps to symbol is typed bar-> in ASCII. For example, inside square brackets, we put the variable I, element of, the set of integers from 1 through 42, maps to symbol, the expression I squared. So this definition defines SQR to be an array with index set, the set of integers from 1 through 42, such that SQR of I equals I squared for all I in that set. Let's look at some different terminology used in programming and math for the same things. What programmers call an array, mathematicians call a function. What programmers call the index set of an array, mathematicians call the domain of a function. Programmers use square brackets for array application. Mathematicians use parentheses for function application. In TLA+, we write formulas, not programs. So we use the mathematical terminology for functions and their domains. However, TLA+ uses square brackets for function application to avoid confusing it with another way mathematics uses parentheses. Many popular programming languages allow arrays only whose index sets consist of the set of integers from 0 to some n. Math, and therefore TLA+, allows a function to have any set as its domain, even infinite sets, such as the set of all integers. Let's return to the spec and jump down to the definition of the next state formula TCNext.
This formula is true if and only if there exists, typed \E in ASCII, there exists some R in the set Rm for which this subformula is true. Suppose Rm is a set whose elements are the four strings R1, R2, R3, and R4. Then this formula equals the disjunction of the four formulas we get by substituting in the subformula each of those four elements of Rm. The exists declares the identifier R to be local to this formula. We can replace R by any other identifier, for example XYZ, without changing the meaning of the formula. But XYZ must not already be declared or defined at this point in the spec. TLA Plus does not allow defining or declaring a symbol that already has a meaning. Let's now return to the spec and move back up to the definitions of prepare and decide, starting with prepare. Recall the state transition graph of a resource manager. Prepare of R describes the working to prepared step of resource manager R. This step can be taken only when the current state of resource manager R is working, so Rm state of R equal to the string working must be true. The step must change the value of Rm state of R to the string prepared. Most people think that condition is expressed like this. Stop the video and figure out why this is wrong. You have to learn to see what a formula says, not what you think it should say. What does this formula actually say? It says that the value of Rm state of R in the new state is the string prepared. What does it say about the value of Rm state of S in the new state for a resource manager S different from R? Absolutely nothing. The spec can't just say what the new value of Rm state of R is. It must say what the new value of the entire function Rm state is. That value must be a function with domain Rm. And we know how to write such a function. It looks like this, where we have to replace the ... with an expression that specifies the new value of Rm state of S for each resource manager S. If S is resource manager R, then the value of Rm state of S in the new state should be the string prepared. Any other resource manager S should have the same value of Rm state in the new state as in the old state. This is correct, but it's too long-winded. We need a shorter way to write this expression. TLA Plus provides this except construct. Everyone hates it. What does the exclamation point, usually read as bang, mean? It means nothing. It's just syntax, but you'll get used to it. So here's the complete definition of prepare. Now for the definition of decide. It describes possible steps in which resource manager R reaches a committed or aborted state. It's the disjunction of two formulas. The first describes a step in which resource manager R goes from the prepared state to the committed state. Such a step can occur only if R is in the prepared state. R can commit only if every resource manager is in the prepared or committed state. This condition is written in a formula named can commit, whose definition we'll look at later. And in the new state, R is committed, and the state of every other resource manager remains the same. This is expressed with our friend except. The second disjunction describes possible transitions to the aborted state. R can abort from the working or prepared state, so Rm state of R must be an element of the set consisting of the two strings working and prepared. R can abort only when no other resource manager is committed. This condition is written as formula not committed, whose definition we'll look at later. And the state of R changes to aborted, while the state of all other resource managers remains the same. We now look at the definitions of can commit and not committed. But first, digression. Remember that this formula asserts there exists some R in the set Rm for which this subformula is true. If Rm is this set of 4 elements, then the exists formula equals this disjunction of 4 formulas. There is a dual to this formula in which the exist symbol is replaced by this for all symbol, type \A in ASCII. This formula asserts that for all R in the set Rm, this subformula is true. If Rm is this set of 4 elements, then the for all formula equals this conjunction of 4 formulas. Now to the definitions of can commit and not committed. Remember that can commit should assert that every resource manager is in the prepared or committed state. This formula asserts that for every resource manager R, the value of Rm state of R is either the string prepared or the string committed. Remember that not committed should assert that no resource manager is committed. This formula asserts that for every resource manager R, the value of Rm state of R doesn't equal the string committed. Let's take another look at the definition of decide. Replacing can commit by its definition doesn't change the meaning of decide of R. Here's the definition of can commit again. Replacing can commit by its definition yields this formula. We have to change the bound variable R used in the definition of can commit to some other variable like S to avoid a name conflict with this R. Similarly, we can replace not committed with its definition. Definitions provide a simple and powerful way of hierarchically decomposing formulas to make them easier to read. Whether a decide of R step is possible and what it can do depends on the states of all the resource managers. How can this be implemented? What programming language allows a single step to examine the states of a whole set of processes? We don't care. We're writing a spec of what transaction commit should accomplish, not how it's implemented. The next video provides a protocol for implementing it. Let's take one more look at the original definition of decide. Decide of R is defined to be a disjunction of 2 formulas. We could give a different name to each of these formulas, say decide C of R and decide A of R, and in the definition of TC next, replace decide of R by the disjunction of decide C of R and decide A of R. There are lots of different ways to decompose a next state formula into subformulas. In the toolbox, create a new model for the tcommit spec. The toolbox reports that it found 3 errors in the model. Clicking here raises this report. These 2 errors occur here. They're indicated by these little red X's. Since we didn't use the default names init and next for the initial state and next state formulas, you have to enter those names. Enter them now. This error tells us that the model has to provide a value for the declared constant Rm. Go to the What is the Model area and double-click on Rm. We now tell the toolbox what value the model should assign to Rm. Make sure Ordinary Assignment is selected and enter the value here. You should usually start with the smallest possible model, which in this case means letting the set Rm have only a single element. But this spec is so simple, let's make it a set of 3 elements. The actual elements don't matter. We could let it be a set of 3 integers, but I prefer to use strings such as R1, R2, and R3. Type this value and click Finish. We first check that the spec is type correct by checking that TC type OK is an invariant. Add the invariant TC type OK to the model. A behavior satisfying the spec should terminate when all resource managers have committed or aborted. As we saw in the simple program spec of the third video, this means we have to tell TLC not to check for deadlock. So, uncheck this box and click on the green arrow to run TLC. TLC should find no errors. Always be suspicious of success. Check the statistics of the TLC run. Did TLC find a reasonable number of states that can be reached by behaviors? The coverage section reports how many times different sub-actions of the next state formula were used to generate new states. You can double-click on a line to see what sub-action it refers to. A count of 0 means that the sub-action wasn't used, which usually means there's an error in the spec. You should check the invariance of conditions that should be invariant. One such condition for the tcommit spec is the following. It's impossible for one resource manager to have aborted and another resource manager to have committed. This condition is expressed by formula TC consistent that's defined in the module as follows. For all R1 and R2 in Rm, it is the case that, this is an abbreviation for all R1 in Rm, it's the case that, for all R2 in Rm, it's the case that, it is not true that. This negation operator is written as exclamation point in C. In TLA+, it's written as tilde. So, TC consistent asserts that for all R1 and R2 in Rm, it's not true that Rm state of R1 equals aborted and Rm state of R2 equals committed. Add the invariant TC consistent to the model and run TLC on the model. TLC should find no error. The scope of for all and exists extends as far as possible. For example, this expression extends to the end of its enclosing expression unless explicitly ended by enclosing parentheses or similar brackets or braces, or by the end of a conjunction or disjunction list item, which adds implicit parentheses. For example, this expression is parsed as if these parentheses were added, which is easier to read if we indent the second line. So the expression is illegal because this x, which is declared in the inner for all, is already declared in the outer for all. And in TLA+, it's illegal to redeclare an identifier that's already declared. Let's now look at comments in TLA+. TLA+ provides two kinds of comments. An end-of-line comment begins with \***. Other comments are enclosed by these delimiters. Box comments like this look nice when they're pretty printed. It's easy to type boxed comments using the toolbox's editing commands. To find out how to type boxed comments, see the toolbox's help pages. To do that, click Help, then Dynamic Help, then click Contents. Open the Toolbox User Guide and find the Editing Modules page. On that page, go to Editing Comments. The Editing Modules page also has lots of other useful information. You can make a spec easier to read by adding horizontal separator lines like this. The line is pretty printed like this. These lines are purely decorative. They go between statements. The specification of transaction commit, like the die-hard specification, is very simple, but it moved us a tiny bit closer to real computer systems. And you've now learned a lot of the TLA+ you need to specify those systems. Next, we examine two-phase commit, an algorithm for implementing transaction commit.